Good morning. Hope you're doing well today. I'm Ben Cohn. This is my AP Calculus class. This is class number 3. Today we're going to go over the product rule. We've already gone over the idea behind limits and the general idea of a derivative. And so today we're going to go through some of the various ideas behind the derivative, specifically the product rule. But first, let's do a quick review. So here's a kind of question we might get. Let f be the function defined by f of x equals square root of quantity x minus 2, absolute valued for all x. Which of the following statements is true? Okay, so first thing we need to do is visualize what this graph actually is, what it means. So this minus 2 part, that basically moves the whole graph a little bit to the right. And the absolute value square root just allows it to handle negative numbers. So the absolute value makes everything positive, and the square root, that just square roots things. So a square root graph normally looks kind of like this, where y equals x is kind of like that. Square root of x is generally a little bit less. Probably actually is kind of like this, where when you're between 0 and 1, the square root is actually greater than y equals x. But once you get above 1, the square root of value is less. It looks kind of like a little. Okay. So we go 1, 2, and we look something kind of like this. And we're going to get a sharp point down here because we have this absolute value thing. Absolute value sign operation, so to speak. And so that's why we're going to get this sharp point out down right here. Kind of sort of bounces almost off the x-axis. So you can put this in your calculator if you have a portion where you are allowed to use a calculator. You usually have about 30 minutes for those questions. This would probably not be a calculator question. And even if it was, you really should try to avoid using a calculator for this. And you should be adept enough at looking at functions. They should be like, okay, this is kind of what's going on here. But just to make sure we get a clear view of what's going on, I'm going to take a look on Wolfram. So we have, let's do y equals square root of absolute value of x minus 2. X minus 2. Thank you, Wolfram. You are my hero. Okay. So yeah, it looks kind of like what you said. It comes down, goes to a point, then goes back up. So that's what we're looking at here. And so now we're trying to find out which of the following statements is true, i.e. not false, or at least possibly correct. So f is continuous but not differentiable at x equals 2. So x equals 2 is right here. We plug in 2 up here, and we have 2 minus 2, which is 0. Absolute value of 0 is 0. Therefore, when we take the square root of 0, we get 0, because 0 times 0 is 0. And so if we look at it, it says it's continuous but not differentiable. So continuous basically meaning we can draw this without picking up our pen. That's true, we can. But differentiable means there's a slope. So if you look at the slope, you get a feeling that it's probably actually going to be going down, or at least probably actually straight down coming from the left. But then it's going to be going upwards, probably straight upwards, going to the right. And so you're not quite sure if the slope is going to be up or down at x equals 2. And since you have that ambiguity there, the derivative won't exist. So that the first question, part A, probably true. That's probably the one that is true, because it's not differentiable, i.e. you can't find one specific value that is the slope. So when they say continuous, means you can draw it without picking up your pen. And differentiable means that there is one unambiguous definitive slope at that point, which there isn't. And pretty much whenever you have a graph and you see something that's pointy, any sort of pointy, that generally means not differentiable at that point, because it means there's a sharp turn in the graph, and that sharp turn or instantaneous turn is basically means that slopes are not going to be the same coming from the left or coming from the right. So this is probably going to be the answer. We'll circle that as a potential. whoop, f is differentiable at x equals 2. Nope, we already decided by the first part that that is not true. F is not continuous at x equals 2. F is continuous at x equals 2 because we can draw it without picking up our pen. I know that doesn't sound like a very formal definition, and it's not, but it's a great definition and works well for this class. Pretty much works for everything too. Okay, limit as x approaches 2 of f of x does not equal 0. No, it does equal 0. So if you have 2 plus, which is slightly bigger than 2, minus 2, you're going to get 0 plus. And when you take the absolute value of that, it's going to be 0 plus still, and then you take the square root, and you're still going to get 0. So let's say you have 2 minus, slightly less than 2. You subtract 2, you're going to get slightly less than 0. But then you take the absolute value of that, and you're going to get 0 plus, which is slightly bigger, infinitesimally smallerly bigger than 0. And you take the square root of that, and then you're still going to get back to 0. So the limit as x approaches 2 from the left and the right are the same, i.e. you have this from the left negative, from the right positive, and since they're the same, that means that limit as x approaches 2 f of x does exist, and in fact does equal 0. So this exists, but it equals 0, not equals 0. And then x equals 2 is a vertical asymptote of the graph. An asymptote means that there's some sort of line, or at least some sort of function that you're approaching, that it approaches but never quite reaches. So when you think of a vertical asymptote, you think of something like something that x cannot equal. So like 1 over x minus 2. X cannot equal 2 in that case because you can't divide by 0. But for this, x can equal 2. If you plug in 2, 2 minus 2 is 0. You can take the absolute value of that, which is 0, and you can take the square root of that, which is 0. So asymptote means one of the key characteristics of an asymptote is that you can't actually equal the asymptote. In this case, you can equal, x can equal 2, so that's not true. So high confidence that A is the correct answer at this point. And then you say A is the answer, it is, and then you move on with life. And that's how you approach some of the ideas behind continuity and being differentiable. Okay, so that is our review portion to make sure we kind of solidify, ossify, make hard, solid, secure our previous knowledge. So now we're going to talk about the product rule. So we already know the power rule. So if you say that f of x equals, I'm going to be more generic here, x to the n, then we know that f prime of x will be n x to the n minus 1. And we derive that and showed that why that's true. The purpose of us deriving it was not really so you know the proof, but so that you know how these kind of things are approached. And the definition of the derivative is x plus h minus, whoa, craziness, no. F of x plus h, a little bit more real estate, minus f of x all over x plus h minus x. And a lot of people just write this as h on the bottom without the x's, which is fine. And this, in reality, is just the slope, delta y over delta x. Okay, so now though, the product rule, I'm just going to throw it up there. Usually when you're taught these in calculus classes, it's just like, hey, here's all these rules, memorize them and use them, which is a legitimate way of doing it, but I like to take a little bit more time and go through kind of the idea behind each of them, because that way when you go to integrals, which are just going derivatives backwards, things kind of click a little bit better, just because you have a little bit more familiarity of the bricks that make up your pyramid. So if you have f of x equals u times v, where u and v are functions of x, so u of x, v of x, and you take the derivative of this whole thing, oh, not yet. Take the derivative, that little apostrophe there meaning the derivative. We could also write dy dx. I guess we could probably also write df of x over dx as well. All the same, just different notation for the exact same concept. Then this would be u times v prime, where these are implied to be functions of x, like up here. And this would equal uv prime plus u prime v. And so to look at an example here, we could say something like, all right, f of x equals 2x cubed times 5x squared. And your first thought is, you're like, well, and solve this. And your first thought is, well, they're just polynomials. We multiply them together and then we do the power rule. Yes. In reality, that's exactly how you would do this. But we only really know the power rule so far. So there's only so many crazy combinations I can come up with. Well, that I guess anyone could come up with. That would do a good job of showing this product rule here. So let's do them one piece at a time. So we have u equals 2x cubed and v equals 5x squared. And this is the procedure or algorithm that I use pretty much every time I do the product rule. Sometimes I just do it in my head, but especially if I have time, I like to write it out like this, where u is here, v is here, and then we take the derivative of 2x cubed, which would be, we bring the 3 down, so it would be 2 times 3, which is 6. It would be 6x squared. V prime equals 10x. Then I write up the product rule. Sometimes I write the product rule up first. Equals u v prime plus u prime v. And I recommend just memorizing this. We'll go through kind of the justification about why this works a little bit later. But it's not worth your time to go through and derive it, especially when you're under pressure. You want to have this memorized just cold. Boom. Take a piece of paper out, write it out a dozen times until it's just burned into your soul. So now we have a v prime, a u prime, and a v. Then we can do the product rule. So f prime of x would equal, let's do u 2x cubed, okay, times a v prime, which is right here, which is 10x, plus a, what is it, u prime, 6x squared, plus, no, multiplied by 5x squared, right there, whoop, whoop. And then, here we multiply these out, we have 2x to the fourth, 20x to the fourth, plus 30x to the fourth, which gives us 50x to the fourth. Okay? So the derivative of 2x cubed times 5x squared will be 50x to the fourth. Now, the thought process then is, okay, so is that true? Maybe? Let's use the power rule to do the exact same thing we just did. So multiply these together, we have 10x to the fifth. Take the derivative of that, f prime of x equals, so then we take the 5 multiplied by the 10, we have 50x to the fourth. That is the same as that, and there's sort of like, okay, maybe this is actually true. Maybe this is the way things work. So here's the product rule. Memorize the product rule. And now, now that you have it memorized and burned into your soul, let's actually look and see where this comes from and how we get it. All right, let's clean up our real estate here. Whoop, 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 whoop. Delete. All right, so, purple. So we have, let's say, f of x equals u of x times v of x, and we want to find f prime of x. So first thing we do is like, well, f prime of x is f of x plus h minus f of x all over x plus h minus x. Okay, so now then what happens when we plug in u and v here? So what we get then is u of x plus h, v of also x plus h, minus u of x, v of x, all over h. So this is pretty standard. Okay, definition of the derivative, plug in the values for the function, and pretty straightforward. Now I'm going to do something. You're right. I will just do it just down here. Good idea. U of x plus h, v of x plus h, pretty standard. Change colors to add crazy emphasis. We will subtract u of x plus h times, nope, not yet, b of x. Then we will add u of x plus h times v of x. And then we'll go back to purple, minus u of x, v of x, all over h. Okay? And from here, you're like, well, how did you just throw that in there? There's two things, and there's more than two. But for the most part, there's two things you can always do in math. You can always add 0, and you can always multiply by 1. And so in this case, what we did here was this right here is effectively adding 0, because we added u of x plus h times v of x minus u of x plus h plus times v of x. And you're like, wow, that was crazy random. Where did you get that? Well, some guy probably smarter than me, almost definitely smarter than me, figured out that this is a proof of way of doing it, and it kind of sort of works. And I know that's not very satisfactory. It's like, what? How? Yes, trust me on this one. You throw this in there, you look at this, you're like, okay, so let's take u of x plus h, is that right? That's probably right. Multiply by v of x plus h minus v of x, x plus, and let's clean these things up a little bit. And maybe not that one, because I might still need that. Get rid of those. There we go. Back to blue. So we factored out the u of x plus h. Now we need to factor out the v of x. So then we have u of x plus h minus u of x. U of x. Scooch over just a little bit. Okay. And then we'll divide by h. But since the h is on the denominator, I can kind of put it wherever I want. And I'm going to put it like this. And so what I did was since two of the numerators were added together, you can split that up and split the fraction in two. Algebra. And so when you look at this, you have u of x plus h. And u of x plus h is basically the same as u of x. So this is just going to be u. And the reason you can do that, and you can't do it other times, the idea here is, I need to choose a good color, blue, light blue. And I can do a better u. U. When you have something, so you have like, well, say this is u, and this is u plus h. U and h are basically the same size. The only time their differences really come out as in contrast is when you subtract one from the other. Instead of getting 0, you have this h left over here. And so the idea here is when you have u of x plus h, you can be like, well, that's the same as u. But when you're subtracting one from the other, what you get is you run into that limits indeterminate issue where it's like, well, it's almost 0, but not quite 0. And then you get a big issues with that. So we can say here that u of x plus h is the same as u of x, which we're just going to write down as u. Now this is the derivative of v. That's the definition of it. So this would be v prime plus, over here, we then have v times u prime. So rewriting this, u v prime plus u prime v. And that is f of u v prime. And so that's the idea of where this product rule comes from, and the idea behind the product rule. So clean up the real estate really quick. So that's a more formal derivation of where it comes from. And again, the interesting part there is you start with the definition of derivative, f of x plus h minus f of x, all over x plus h minus x. And then you just plug in u and v. You do some algebra, you shake up the box a little bit, and eventually you look at the box and say, oh, it's perfect, excellent, that's what I wanted. So there's nothing particularly complicated or mysterious or magical. It all comes from the definition of the derivative. So granted, when you're doing the AP exam, you don't have time to go through this derivation. And this understanding is only kind of sort of useful for the AP exam, especially the derivative portion. But this sort of concept and thought process really comes in value when you're talking about questions where it's like, I have no idea what to do. Like, this thing just boggles my mind. You just start from the beginning, you start making small steps, and eventually you solve the problem. And that's the same idea here. I have no idea how to find the derivative of a product. What's the product rule? You just start from the beginning and say, okay, well, what's the definition of a derivative? Plug in a product, do some algebra, and succeed. So idea, start from the beginning, work your way out. Now let's look at this from a slightly different angle. I'm going to say a more conceptual. Ooh, I can do a square. Square. Ooh. I'm good with that. Okay. Ooh, very nice. Ooh, black square. Okay. So we're going to do something a little bit different now. We're going to talk about the same thing, just from a different angle. And I like to think of things from as many angles as possible, because the way memory seems to work, at least for me, is the more ways you can tie something in, the more angles you can come at something from, the better you'll understand and the easier it is to remember. And so if you have like 6 or 7 different ways of remembering the product rule, and you forget 5 or 6 of them, then you can still remember one, and then it kind of help you remember everything else. And so making as many bridges to that memory as possible kind of helps out. Another idea is when you're trying to memorize things, like the way mnemonics work, try and think of different senses. Do like, well, here's a smell, here's a taste, here's a feel. And that helps with mnemonics too, because you get different senses, different types of memories, and it helps you retain something. Help you do the recall, the stuff it in your head. It helps relocate the penguins onto the iceberg, so to speak. Okay, so what we're going to do here is we're going to say we have the product rule. That's supposed to be a straight line. But this time, we're just going to say u equals x and v equals x, just for simplicity. They could be bigger. That's okay. We're just going to go simple here, straightforward. So f of x total just is x squared. So we're going to say this box equals the product of x and v. So this will, or u and v, u and v. And so this top part will be u, side part will be v. And so I'm going to say this is x here, this is x here. And then we're going to do the derivative, I'm going to say this is h here, h here. So what we're doing is we're multiplying x plus h times x plus h. And we're trying to look at the product of things here. So we're trying to represent the product, u times v, by this box. And if you think of it, if you have a length times another length, then these two lengths multiplied by each other will give you an area. And that's the same thing we're doing here. And so if we take these and we're trying to find the difference in area between the big box here and the small box there, then we'd get something like x plus h quantity squared minus x squared. We can then expand this binomial by either just doing the FOIL, first outside, inner, last, or we can just look at each individual box that's kind of represented here. So this big box will be x squared. These side boxes, we'll have 2 of them, will be x times h. So we'll do plus 2xh. And we'll look at this last teeny box here, which is represented by h squared. And we still subtract off x squared here. And then just to kind of complete our concept here of dy over dx, we're going to divide by h, say the limit as h approaches 0. I know it looks like an n. F prime of x equals this. Simplifying things a little bit, we can cancel out the x squareds, rewrite this. I'm going to drop the limit as h approaches 0. It's still there, but I just don't want to write it again. So then we have h times 2x plus h. Cancel out the h's. Oh. This h goes to 0, and we are left with 2x, which we already knew as the answer because by the power rule, which we discussed earlier, 2x would then go to, or x squared would then go to 2x. So at this point, you're probably thinking, logically, it's like, well, if we can use this to find the product rule of like u times v, why don't we just make a cube? And then we'll find the volumes instead of the areas. And can we do that to find the, I'm not sure what the product of three things is, the tri-product rule, something like that. And you're totally right, you could totally do it, but it's not really worth your time because when you look at it, let's say you have, and let's clean some of this up. Sorry, square, I grow wary of your presence. Nope. Good try. Go away. So if we have something along the lines of f of, let's see, u v w. I know that looks terrible. It looks like a backwards n. Trust me, it's a u. So we have f of f u v w. We could say that this is actually f of u v times w. And so then what you do is you have the product rule of u v times w. And so you do the product rule of that. And then when you have to find the derivative of uv, you then again do the product rule. So instead of trying to find the volume of a cube with all these different sides, and then h as it's approaching 0, you're better off basically separating your three variables into a 2 and a 1, and then from there, then you'll do the product rule once, and then you'll do the product rule again. So instead of trying to think of a special product rule for three variables, you're better off using a product rule twice in a row. And that's the idea for a product rule. So you might be thinking at this point, well, this product rule isn't so bad, I get it, blah, blah, blah. True, yes, it's not. And you're like, well, what kind of questions are going to be asked on an AP exam about the product rule? And the answer is you really won't be directly. So a lot of the questions you'll get asked will use the product rule as a portion of the question. So you might have a question that tries to address 3 or 4 basically parts of knowledge, kind of like you saw when we had questions on limits and continuity and derivatives, like the word problems. Those are really asking us to talk about limits, to talk about continuity, and talk about derivatives. And they're asking us 3 conceptual questions basically in one. That's the same sort of thing you'll have with the product rule. You use the product rule in conjunction with other rules. And so you won't be tested over the product rule directly. It'll be kind of part of a bigger plan, so to speak. This is how we approach the product rule. And next time, we're going to go over the chain rule. So we have the power rule, the product rule, and the chain rule. And those are the 3 main rules you kind of have to learn, understand, and memorize for AP exam. So this time we went over the product rule. Next time we'll go over the chain rule and tie everything together. So the chain rule deals with nested functions, and we'll see how that works next time. So I appreciate you stopping by. Hope you enjoyed it. Hope you learned something. And I will see you on the next one. Thank you much.